So now that we've discussed the problems critical sections and lock brought about, are there other different ways of implementing the coordination that we need among multiple threads? To explain that, we use this motivating example. Imagine a thread is in the critical section, and for some reason it's being swapped out, meaning it's not going to execute for a long time. Or worse still, the thread is dead completely. Now there's a problem. We already gave the critical section holding thread the exclusive permission, and he has something. Everybody else agrees not to do certain things because he is given the permission, and he's dead. We can't proceed. The whole system, the whole parallel code is going to face some problem. So how about we do this a little bit differently? And that's motivating a whole bunch of these non-blocking algorithms, which is don't give mutual exclusion ahead of time. Why don't you do the work and we reduce that into one atomic action to put the result into the system? I'll give you an example. Suppose we have this concurrent data object. What that means is there are multiple threads that can access this at the same time. It's a doubly linked list. I have a pointer, ptr obj, pointing to this object, this whole thing. Okay, it's in the yellow box. Okay, it doesn't have to be a linked list, by the way. Any data object, graph, whatever, you can put them into a container in the notion that they're all connected together, and I have a one big pointer pointing to where it is. How about we make a copy of it? Okay? But before we make a copy, we want to make sure that nobody else is changing the object while we're making our changes. So we're going to put everything in a load link store conditional atomic block. So we're going to make a copy, a local copy. This means we're going to put it into a data structure nobody else is going to touch. Now other threads is going to touch. Well, making a copy is easy. Boom, 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 we get a copy. Okay. This copy is not the same thing as before, but it contains the same information. So be it a graph or a linked list, the semantic content is the same. But all the pointers, all the locations of the individual elements obviously are different. Now it's in a different yellow box. So now we go ahead and do whatever we want to do in this non-concurrent object. It's a local copy, nobody else is going to touch it, so by definition we have our sort of mutual exclusion. Maybe it's deleting an element from the linked list. So we perform that sequentially. Now we have a new data structure, specifically the second one. Maybe I should have put it into a slightly different color, but this box now has the correct data structure, has the correct content. How about we, okay, so sorry, there's a little animation, right? It's more than one step. That's why we did it sequentially. Now we're done. This whole thing is done. How do we make this? And at this point, we're not doing anything in a critical section by requiring a lock and waiting for other people to give us permission, okay? And then in one single fell swoop, we point this global pointer to this new copy, okay? That's all you're doing. You're moving the pointer to the local copy into the variable ptr obj. Now, if someone changed it ahead of you, the store conditional would fail. We would presumably go back and redo this trial. But that's the idea. We do the work and submit it atomically, rather than getting exclusive permission to work on something, precluding other efforts to touch the object. Well, there's lots of issues with that. It's seemingly elegant and simple even, but there's a problem, and we will see this problem coming back later on when we touch upon the concept of transactional memory. But I'll give you a preview here. So yes, this will fail if someone else came in and changed the concurrent object. For instance, point the object to his local copy. But there are side effects of this. Once the copy is changed into this new copy, let's say another thread created, I don't know, a red version over here, and instantaneously, or using this store conditional to move the global pointer. Meanwhile, I am still doing the local copy. So I'm still copying this element here, this element there, this over here, and so on. But you see, this concurrent object is no longer useful. It's dead. I just don't know it. I haven't done the store conditional. I'm still doing a loop, making a local copy. Okay, so what can happen? Well, what can happen is this memory is reclaimed and allocated to something else, and in that something else, let's say, created a whole bunch of and it's not even a pointer, it's a whole bunch of data element that doesn't even make sense in the original data structure. It's reclaimed. It's a picture that puts in. I'm still treating it as a linked object. So maybe it has an infinite loop in its data structure that I don't know that can possibly exist, and I get stuck. Okay, so this copying is a problem. Now, we're not solving the problem here. It's beyond the scope of this class, but this is the general idea. Now, it's not as simple as it might seem. Not to mention there are other issues, like, okay, I have this gigantic linked list. I just want to get rid of the first element, to dequeue the first element. Now, with this type of operation, I have to make a whole copy before I can make one small change. So that's clearly not efficient. Okay, so this is not a solution that is a straightforward improvement. It's a trade-off. In general, these type of algorithms that do not use logs are called a log-free implementation in a very generic way. It's not better. It's not better in all respect. It's a trade-off. It's better in some respect, more costly in some other respect. In general, a better way to think about it is that it is a more robust solution. Okay, but there are different levels of robustness, it turns out. And again, we had a seminal paper on this on the website for you to look at. But we're just going to get a very, very shallow kind of superficial understanding of it. Okay, so as it turns out, there are different levels of robustness, and the very basic version, if you wish, it's just non-blocking. Why non-blocking? If the thread who wants to change dies or swapped out, it's not going to block anybody. So if you just want 2,000 thread to work on concurrent data structure, one thread is killed for some reason, no problem. The other 1,999 will make forward progress. Non-blocking, because we're not using log. But if 2,000 threads are using log, and it just so happens the thread that dies is holding a log, then your entire parallel operation has to terminate. It will not make forward progress. But this doesn't mean anybody is going to, or nobody's going to have a starvation problem. So here, you can imagine a poor guy keep on making copy, and just before it tries to do this, someone else came in and store conditionaled a new version of it, and you will fail, and you will have to loop back and retry. And in the extreme case, one guy can never finish what he wants to do. And so there is a more robust version that's called a wait-free algorithm that guarantees all processes will complete their operation in a finite amount of time. So there is no starvation. Okay, so how do you do that? Well, again, that's beyond our scope, but the general idea is everybody sort of announces what they attempt to do. And so the winning bit somehow, the winning thread who succeeded in doing something somehow will help you out, even if you failed store conditional. Okay, it's doable, it's not easy, and it's another level. So it's a stronger guarantee. And obstruction-free is somewhat weaker than that. It guarantees progress if no other thread is running. So it says, I'm not guaranteeing you're wait-free, but I am guaranteeing that you're wait-free, or you don't have a starvation problem if no other thread is running. When there are other threads running, I can't necessarily guarantee you that. So this is to separate the two. So, okay, fine, there are these operations. And this is sort of the same in the general idea of this notion, transactional memory, and that's an idea proposed back in 1993 as a piece of hardware. And in the early 2000-ish, or perhaps slightly earlier than that, it was sort of re-embraced, generating north of 1,000 publications in short order, people proposing different implementation, optimization, and even semantic models. Okay, so we're going to have, again, a whirlwind tour of this whole concept. I don't do research in this area, so I cannot guarantee that everything I say is correct. It's just my interpretation after reading the summary of a lot of these papers in a book. So we just want to point out that there is this group of solutions, and you will see at the end what some experts think about this group of solutions. But anyway, the idea is we provide some sort of mechanism to tell you that I want certain things to be done atomically. And we'll call that a transaction. You'll see why. So something like begin transaction, end the transaction. And if you do that, you're expressing to the hardware you want atomic operation. But you're not saying I want to grab that particular lock. Okay, so you're expressing desire rather than its implementation. Inside your transaction, you can load normally, but you can also load transactionally. You say, okay, this is a transactional load, which means if the transaction is not atomic, for some reason, it cannot be carried out as if it's an atomic thing, indivisible in time. It all happens, or it doesn't. If it cannot be done, then these transactional memory operations have to be aborted, as if they have never been done. So you have load exclusive, store, and they're all done transactionally. Meanwhile, you even give the software the ability to declare to abort if you want. You can ask it to try to commit, to say I'm done, and see if it can. So it may not be able to commit for whatever reason. We'll get into that. So you have these state instructions. You can say, am I still valid? If so, I want to commit. Did I commit successfully? If not, I want to abort. So hardware provides these kind of primitives, and then the software can use them to express the desire for atomic operation. So what is a transaction? What atomicity? So here's a simple example, right? I want to increment the counter. What do I do before? I grab a lock. So the code has to have a lock dedicated to this counter increment, and everybody has to go through the lock. If you did it wrong, too bad, you have a bug in your code, right? What we do now here, none of that. We have the counter, and we're going to try to just increment it and declare the need for this to be in an atomic effort with respect to any access we might have encountered in the code. So what does it look like? I simply say this. I want to load this. Okay, I want to load, but I want to write to it. So I would use a load with an intention of exclusive access. This exclusive access is not, lock, this atomicity exclusive, but exclusive as in cache coherence. I want other people to also get rid of their copies because I'm going to write later. Sort of like a prefetch with intention to write. So, okay, I load and I increment by 1 and I store it back transactionally. Okay, what I want to do is to finish this transaction in an atomic fashion with respect to another effort that touched counter. If I succeed, I'll try to commit. If I succeed, great, I'm done. If I don't, I want to come back and try it again. So what do? I use a random number, okay, and I have a back off counter. And every time I failed, I increment my back off counter because this is shifted by that amount. So this is an exponential. Every time I'm doubling the amount of cycle that I'm possibly backing off, okay? And the more I fail, the more I increment. I'm likely to wait some amount of time, okay? And I will not back off beyond a certain range, but if I'm still beyond that, I'm still within the range, I will simply increment my back off. And if I succeeded, then I simply reset the back off counter to very small so that next time I can try without a lot of back off. Okay? So that's how we intend to use these hardware primitives. And the idea of a transaction comes from database. A lot of things in system design may have this inspiration from database, which had the same problem. And then in fact, database transactions, every time you do something, you have a database maintaining, I don't know, the your inventory of something. So you may change this by saying part of the inventory was sold or transferred, and any effort to modify that database is in the unit of a transaction. Okay, not just like just like in trade, it's a transaction. You give me money, I give you the product. So usually there are a whole bunch of requirements, and they kind of like to make it sound nice. ACID, 4 distinct things. Atomicity, this simply means all or nothing. You cannot have half of a transaction. So you cannot leave behind garbage. Instead of adding 1 to this, adding 3 to that, you only added 1 to this. Can't happen. Consistency is about the database itself. Okay? A transaction comes in, will modify the state. Now the state of the database can only go from one valid one to another one. You cannot stay in the middle. For instance, I have a linked list and I have a count. And if I deleted the last element from the list, I want to set my list pointer to null, and the count has to be 0. So, but I'm doing this one step at a time. So the intermediate step where the list is pointing to null, but the count is still 1, is a transient state. You cannot allow that to happen. You cannot allow that to be your global state. So your consistency says the database goes from one stable state to another. It cannot stay in transient state and viewed by another transaction. So the transient state cannot be seen by another transaction. Isolation means two transactions are not happening at the same time. Okay? They cannot be going on at the same time. So this is sort of what we kind of try to imply when we say, oh, it's atomic. Okay? It has no size in time, so the two of them cannot be happening simultaneously. This is just more explicit to say the transactions are not happening in parallel, and so the implication is they're serialized. One happened before another. Whichever one doesn't really matter as long as they're serialized. And finally, if your transaction is committed, and then the power is gone, too bad, right? The database might be in a mess. No, that we cannot allow that. So you need durability. So even if there's a crash, somehow there needs to be mechanism in place to make sure that it's forever, even though the thread died. So in transactional memory, or TM for short, we're mostly talking about the similarity with respect to database transactions on ACI, not the durability. After all, it's transactional memory. The memory is a transient thing, at least, at this point. We're not talking about persistent memory yet. So no support, no promise of durability. Okay, we're just talking about atomicity, all or nothing, from one solid stable state to another, no transient state exposed to another transaction, and two transactions are always serialized. So how do we implement this? Well, usually the atomicity and isolation, they're relatively straightforward to implement. Okay, it's usually the effect of whatever you're doing can be reduced to one action, and therefore that one action is somewhat already atomic in a hardware implementation, or in a system implementation, I should say, and we just have to make sure that that happens. So for instance, there are two flavors of this, right? The hardware version or the software version. They're pretty much similar in respect, in this regard, how this is done. Let's say I have a hardware implementation, and I have a transaction that writes to memory location X, Y, Z. What do? I somehow put them in buffer. And if I find out that this transaction can be committed, I can make them valid in one shot. Okay? For instance, I can declare that I can have a speculative bit in my cache for some data that I'm writing to, and later on, when I realize I'm done and I'm allowed to commit, then I, in one go, get rid of all the speculative bit, and boom, my data is now in the system state. And anybody who wants to read the new value will have to come to me, because now I have the newer copy. I just wrote to them. In software version, this is usually done just like the animation that we had, right? We have a data structure in yellow box, we make a local copy, and we do something to it. That's not necessarily atomic, but we're doing it on a private copy, so nobody is, it's atomic with respect to another effort on my local copy, which is nobody. Nobody is working on my local copy, so my effort is atomic. And then I do a compare and swap and just put it in place. So atomicity and isolation are relatively easy. Well, this is the atomicity part of it. The isolation means you cannot have transactions happening simultaneously. So if one happened, the other has has to happen afterwards. So all of a sudden, if I have a read to memory location X, and before I'm done, someone else wrote to X, and that transaction committed. And I have to be seen as if I'm happening after him. Now what do? I already read X. It was an old X. Okay? Well, too bad. We can kill you. So let's go back to the atomicity part. The other side of the atomicity is if I am to fail, what do I do with respect to the things I already wrote to? Well, they're temporary. That's what buffers mean. Okay, in the software version, too bad. You had a bad local copy. Just get rid of it. Retry. So, is this easy to implement? Yes, in principle, but there are problems. You have a transaction, wrote to a lot of things. Where do I buffer them? And a very straightforward answer to that is in a hardware transactional memory, buffer them in your cache. Okay, just put a speculative bit. But what if you have a big transaction that it's overflowing my cache or there's a conflict? Okay, and then I have to have some spilling mechanism. I have to worry about all of that. So it's not trivial. It's doable, but it's not trivial. The isolation aspect of it is to say I have two transactions, they have to be seen as if one happened before another. They have to follow a serial order. Actually, it turns out there's a lot of debate about the semantics of what serial order. Okay, and as long as the strict sense of isolation simply says a serial order, any serial order, it may not have to make sense, but it has to follow a serial order. Suppose I have 3 transactions. Okay, they're actually executed concurrently, A, B, C. One of them is the increment counter, one of them is the decrement counter, and the third one is to reset it to 0. Okay, so then if you think about it, A, B, C, suppose they actually happened in that order because I did something else and I can tell C happened after B, the isolation aspect says, oh no, you don't have to follow any particular order, any one that is an order. You say, I observe that the transaction goes like that, ABC. Since C is a reset, the final state of the variable should be 0. But I have this transaction and I somehow managed it and the outcome is -1. It didn't violate the isolation part of the contract. Okay, and you will see later on that some people are arguing about these semantic meanings to say why that's allowed to be considered legal. So to me, it's like this just doesn't make sense. We shouldn't even discuss this. But for some reason, people say, well, no. There is a reason for its existence. So let's just give it a name. That's serializability. Okay? It may be bad serializability, but it's serializability nonetheless. So what is a good serializability? Okay, it's something called a strict serializability. This loophole that we were just talking about, no. If in reality A happened before B, then this serialization has to be A before B. You cannot say, well, A happened before B, but I give you the result as if B happened before A. That's a serialized version, so it's fine. That's not strict serializability. I think this is really unnecessary complication in the model, but people are actually writing papers about them. So how do I know that? How do I know the two things are in conflict? What does it mean two transactions are in conflict? That they are not serializable if I allow both of them to commit? Well, if two transactions are reading and writing completely different things, then it really doesn't matter, because the outcome is as if one happened first, another happened later. But if they have a set, a conflict set, meaning a set of address where at least one transaction, both transactions are accessing it, at least one of them is a write, then you have a problem. Then it matters which one executes first, which one executes a second thing. So you need to detect a conflict. You need to detect one transaction's read-write set overlaps with another thread's write set. Okay? And when you detect that, what do? Because now they cannot happen simultaneously, the result will make it look like they're not executed in sequence. Then one of them has to be retried, to be killed or aborted and retried perhaps later. So now you have a policy issue on your hand. What do? Detecting conflict is kind of straightforward in principle again. Okay, just coherence hardware that we were discussing allow you to look into your cache to see if someone is reading something you wrote or someone else is trying to write to something you have read. That part we don't have in the coherence, but you can build it. You can monitor all the things that you read, you can monitor all the things you write, you monitor another transaction's effort, and you can compare them. You know, there are optimizations you can do, Bloom filter, whatnot. You can do that. I didn't say it's easy, but you can do that. And now you can decide to proactively fix the problem if there's a conflict, or do it lazily. Okay? An eager or proactive approach would be the minute I detect conflict, I kill one of the transactions. Lazy one says, okay, let's not worry about it, so long as we don't commit both. When there's a conflict, we don't have to worry about it right now. Let's wait. Maybe one of them is aborted anyways. Then that leaves the other one, so we don't have to pick at the moment. And then you have the problem. Okay, so suppose there's a conflict. What do? Do you keep on doing it? Do you back off? Do you say, okay, I'm gonna be killed, but then if I execute immediately, I'm gonna be killed again, so maybe I should take a walk, just like the back off in the lock. And it turns out people studied this, that in general, if everyone is being polite, it's good for everyone. So you have to figure out. These policies are not trivial. You have to run experiment to see what empirically seem to work well. Commit. Coherence. I'm sorry. C, coherence. What's coherence? Coherence says the state seen by a transaction has to be the stable state, not the transient state. Well, this is actually fine for committed transactions. If I commit the transaction, I change the state from before the transaction to end the transaction. This is all fine. Where's the problem? And the problem comes, is that enough? If we have committed instructions, committed transactions are fine because they're isolated, okay? We already guarantee that all transactions are happening as if one after another. Now, the state will therefore be from before a transaction to after a transaction. That's the stable state. What's wrong with that? Well, the problem is, what if I have a transaction that's in conflict with one that is just committed? So from the point of view of the committed committed transaction, everything is fine. But what about the one that is conflicting with a transaction, and it was committed? Let me give you a specific example. Let's imagine I have a search, I have a linked list, okay, like that, and it's very long, right? And I have a transaction to, I don't know, find an element in it and set its value to 0, okay, to modify a single entry in it. So what do? I have a transaction that has a lot of things that I'm reading. I read this element, and I read that element, and so on and so forth, right? This is a long transaction. And it's called that T1. T1 is doing the search, okay? And, well, if someone else comes in, T2 comes in, and changed the state a little bit, and since it was a short transaction, let's say T2 simply says, oh, you know what, this pointer that points to the head, let's just make it null. Let's make it point to an empty set. Okay, so I come in, I have this, it's easy, I'm done, boom, I'm gone. Okay, as far as T2 is considered, the state was pretty fine. Before, the state is this, that the pointer, let's call that P, is pointing to this data structure. And after T2, it's pointing to that data structure. Nothing in between. But what about poor T1? T1 is now searching this linked list, but this memory is going to be reclaimed, and someone may write junk into it. What about T1? Okay, what guarantee can we give T1 to say you're not going to read something that is very garbage-ish? But this is now nobody's guaranteed. This is no longer useful, and anybody can mess up this piece of memory all at once. Okay, so that's a problem. This consistency or consistency for the data structure is not guaranteed. At least not for the poor T1. Okay? And T1 in the technical term is doomed. It's not dead yet. Depends. It depends on when we'll kill it. We can detect that there is a conflict because the head pointer was changed and T2 is done. So T1 cannot possibly commit. Okay? It will eventually abort, but the problem is what happens to it now? Maybe it will keep on running forever. And that's a problem with the consistency model of the transaction. Okay? That from the perspective of T1, the database or the state didn't go into a transient state. From one stable state to another stable state. It was giving me this garbage view. So that's a problem. And this is sort of like the cartoon that you're seeing, right? It's eventually dead, okay? Like this, what was it, raccoon or Disney cartoon always shows you walk over a cliff, okay, you're doomed, but before you realize it, you may still do illogical things. And it's the same thing, T1 is doomed. Eventually it will be dead, but before that, it's going to do crazy things. What about that? Well, it turns out some of the models people propose treat the behavior of doomed transactions as undefined. There is no consensus on what is the right model. Okay? We define what happens to your transactions that are going to be committed, but not to those who are doomed. Okay, so this is headache too. It's not clear what is the right way. If we propose a complex model, then it's easier to implement on the hardware, but more complex for the software programmer to reason about their program behavior. Imagine you writing this T1 search. Now your code needs to be careful because you could be in a doomed state, And then you're undefined. This thread can run forever. So what do you do as the programmer? You might want to introduce some effort mid-transaction to see if you're still alive. Because if you don't, you could have kind of a live log. You keep on doing things, but it's not making forward progress. Your thread is eventually going to be killed, eventually, but who knows when. So the semantic model, what does it mean to have transactions? Turns out to be a pretty messy bowl of soup. Okay, we'll talk about a couple of issues here. It turns out, and these concepts are usually borrowed from distributed software, database, so it's already out there. People are already using those terms. So these are being introduced to the coordination or synchronization software. Okay, so we already discussed serializability is this notion that all database transactions can be shown in a serial order. Okay, it was this transaction 1 happened before transaction 3, and then it was transaction 2. In the serializability model, actually nothing was mentioned about the failed transactions, those that didn't commit, was aborted. We didn't talk about them. The serializability has nothing to do with failed transaction, and that's a problem. So a stronger model, it's called opacity, that says if your execution supports opacity, not just serializability, then it will be able to show where the failed transaction occur in the serial order. Okay, and another concept called linearizability is from the software point of view. Every time you make a method call, an invocation on a shared object, of course, we can give you in a linearizable execution, we can tell you that happens as if at that point, at point, 325 unit of time. That's the point your transaction occurred. So these are all slightly different subtle concepts that incurred a lot of discussion. So, and in some way, this is analogous to the consistency model thing. If I provide a very weak model, I'm not defining this, I'm not defining this, and as a programmer, you're going to be faced with the problem of, okay, what is a reasonable expectation of my program behavior? This can happen and that can happen. And in a stronger model, I can reason more easily about my code, but the implementer didn't like it because it didn't give them the flexibility in implementation. So lots of these things happen. And in fact, there is perhaps an even more fundamental problem. Okay, we have all these transactions, but in some code, we don't have a transaction. We just have read and write. So they're not really in transaction memory mode. How do you mix them? Can you have both non-transactional memory and transactional memory happening at the same time? Okay, it's very confusing. One school of thought says this is what's happening. If you start a transaction, that's when you're worried about synchronization, right? Like about two threads possibly modifying a concurrent object simultaneously creating a problem. That's why you use transactions. If you don't have a begin transaction, do this, you already know it's not a problem. So the programmer is already guaranteeing us there's no problem. So we can assume the non-TM code that the programmer put down didn't have any problem. We can ignore them. If there's a problem, it's the programmer's fault. We don't have to worry about it. Okay, and then we have these transactions, right? The transactions in a non-TX mode, we just don't worry about them. If they wrote to a location that I have a transaction and I'm reading from, is that a conflict? The answer is no, it's not a conflict. It's a bug. We don't have to worry about it from the implementation point of view of the transactional memory. And okay, let's just give you an example. One way to think about this whole thing is that a transaction, any transaction is effectively a critical section with one gigantic lock. Okay, so you have a code, you have transactions, and you have code where you don't have transaction. Let's just pretend all your transaction is buffeted by a lock attempt and an unlock attempt at the end. And this lock is this gigantic the lock, one single lock. How about that? That's one way to think about transaction. And that will give you the effect that if a code that is outside the transaction somehow changed a variable that your critical section, your transaction is trying to read, that's your problem. You have a bug in your code. Okay, it's not that we have poor definition, but you have a bug. Okay, so is this the only model? No. Turns out people want to mess with models. Okay, I like single log atomicity. At least it's conceptually straightforward. But no, people want something else. They want disjoint log atomicity. I didn't even bother trying to understand these. These are all in the book. I think we have a link to that book, Transactional Memory, a whole book just about this. So that's about the semantic model. What does it mean? What does it really mean when we write transactions? So it's not a simple, clear-cut answer. Different people have proposed different things for various reasons, just like consistency model. Why do we need so many models? Because everybody thinks that model, or whoever proposes a model thinks there's benefit to that model. And it doesn't help the community when you have so many confusing things. Now let me discuss a little bit about other problems. So remember, what was the problem? What was the gripe that we had about lock? We can't do nesting easily. Okay, can we do nesting easily for transactions? Sure we can. How about this? We have a transaction, begin transaction. In this transaction we want to do something, and we want to call another function to do something else, which itself is a transaction. So we have, you see, we clearly expressed our idea in this nesting. In the outer transaction, we need to do two things. Okay, let's just call it A. And in the inner transaction, we need to do something like let's call it B, even though this is just one variable, but B may be a lot of stuff, and maybe A might be a lot of stuff. So when we write a nested code like that, what do we mean? More specifically, if the transaction failed in the inner transaction, do we fail the entire transaction or just that part of the transaction? And if we failed outside, in the outside transaction, but the inner transaction has already committed, then what? And if you pause a little bit and think about it, it's not a straightforward question to answer. So again, we have different models. Model 1, it's called flattened or subsumption. It's at least very clear. You know what? There is no inner transaction. It's just we have to do all these things together. That's it. So the minute we see there's an internal transaction, we ignore that. That's actually straightforward. We know that this is the case. Okay? But then the implementation may be a little bit more difficult because the implementation that had these begin transaction, we somehow have to strip them. Otherwise there's complication. So let's say you failed halfway in here, you don't retry this transaction. You just, the whole thing failed. You have to start from the beginning. So suppose you detected someone else is conflicting with you in your inner transaction. Fine, you fail the entire thing, you restart. But then, okay, other people have other models. One of them says closed. That says this is just like flattened, except the aborted inner transaction does not abort the outer transaction. Okay, it's not a necessary thing. It just aborted the inner transaction, whatever that means. And then I read this somewhere. It says this is so-called open nesting. It boggles my mind. I don't know why this is being proposed. It says if the inner transaction is succeeding, it needs to be seen by the system, even though the outer transaction might fail. Okay, it's just why. Anyway, so now we see it's perhaps an interesting concept. It's not necessarily straightforward. We can all agree on a model and then go and implement this model. And in any case, TM is kind of a productivity tool. So don't expect that to give you a lot of performance, to say, oh, I have TM, so therefore I'm running faster. Well, it can. Like, remember, if I have a log-based system and whoever owns the log died, the whole program essentially grinds to a halt. So it's very poorly performing. Any code that makes forward progress is faster than that. So it gives you, but by and large, in the general case, it's really giving you perhaps an easier time in theory to code. You can express your idea, you can express what you want rather than how it's done. Okay? Log is much more micromanagement. You're not telling the system you want a piece of code to be in an atomic state with respect to another effort. You're saying, I want that log. Okay, so conventional logs are pretty good. They solve, they have problems, but they work. And in a lot of systems, they're being optimized. And yes, productivity is good, but if I saved some time and it's easy to write the code, but the code runs very slowly, that's very bad. Okay, if the but no, it doesn't help that the TM models that are floated out there are conflicting. So I don't know what to do if I'm a coder. But of course, it's not really that bad. It's all in the academic sort of discussion where people are floating different ideas. Some are crazy, but in some finalized practice, maybe we don't use some of the crazy notions. So there are lots of issues to improve the performance, and that's why many papers are being written. So for instance, you want these to be in isolation, but they're not going to be actually in isolation, right? These attempted transactions happen at any time. They will have conflict and this sort of thing. How do you handle them? So a whole big issue is called contention management. How do I try to make two transactions play nice so we don't suffer a lot of performance loss? It's just a big topic. A lot of people spend a lot of effort on these things. How do you write a good contention manager? You can plug and play different versions and see what happens. So there are generally two types. You manage them well, okay, but you avoid unnecessary conflict to start with. Okay, so one of the motivating example is that if I have a sorted list and I'm just going through the list to search for something, so everything I read in theory, would be entered or tracked in a read set. Okay? That's how I know I have a conflict with another transaction. If some other transaction wrote to one of the variables that I read, and then I have a conflict with him. Okay? Then either I abort or he aborts. Right? So, what do? If I have a plain vanilla code, I simply say begin transaction, do a loop, right? Loop, and transaction. Sorry. And this is a very, very, very long loop. And then chances are some other transactions came along, modified some early element in my loop, in my read set. Boom, I'm dead. I have to restart from the beginning. So, but in terms of semantics, I'm searching for something. Okay, the things that I already read, I searched for them. They didn't exist. It's a sorted list. So if someone modified something before I read it, it doesn't matter. So you can, what if you are allowed to release data from your read set? You tell the system, oh no, if someone changes this variable, don't kill me. I'm fine. I can still work. Now you see, then this compromises the purity of the model. Okay, so now this is helping me to improve performance. Sure, I get that, but the whole point of using transactions was that I don't worry about things like that, and the system takes care of it. But clearly, it's not an easy job for the system to take care of it and performing very well. So lots of problems. Okay, I'm just not going to talk about the details. I think this is good enough kind of a superficial analysis of the topic, knowing that okay, it's a possibility, but it's a very complex thing. It's a complex trade-off. So it's clearly not a panacea. At some point, people were kind of making implying that this is going to solve all the problems of synchronization. So the question is whether it is no longer whether it solves all problems, but whether it is useful at all. Okay, there are clearly a lot of kinks to work out, but once the things are fully worked out, are we expected to benefit significantly from it? Well, clearly industry has made their move. AMD had something very early on called Advanced Synchronization Facility. It allows you to write very short transactions, and they work well. And now more and more machines are supporting these. So I was about a couple of years ago, actually 2010, when Azure's chief JVM architect Cliff Click gave a talk in IBM when I was doing my sabbatical there. I thought he had a very interesting slide. Okay? He talked about this, a very interesting conclusion on it. So he explained how they did it, what are the lessons learned from it, and his conclusion is this: transactional memory almost never hurts, but rarely helps. So I think the jury is clearly still out. I think over time it's going to get better. How much better? It's, I think, a matter of perspective, as well as the degree of clarity that researchers can put into their implementations. So anyway, the whole point is synchronization is a big topic. Traditional approaches requires hardware to provide some kind of exclusive access capability. Okay, so and usually that will be enough to allow software people to write these critical sections. So the general solution is lock, and based on lock, we can have barriers, this type of things, and it's usually sufficient for programmer. But transactional memory or lock-free algorithms are an entirely different way of either implementing the lock or expressing the need for critical sections outside of the concept of lock. So these are all being explored. I would say at the moment, just straight lock conventional way is still the typical implementation for this type of need. And next time, so that wraps up the whole synchronization. Next time we'll move on to a different topic.